Okay. So after you get pretty familiar with this, um, you start to see a pattern in all of it. And so this page in the book, 473, provides kind of like a standard issue shear and moment diagram for each scenario that you can encounter. I don't see over-constrained scenarios, but these are otherwise solvable. Um, so point load in the center, point load not in the center. And so these will show you like how to calculate the maxima, the maximum moment here. Um, so like this one's a little bit crazier, right? Because they have that parabola there. And so from our example before, we had a simply supported beam with a distributed load across the entire thing, and it was at 3 kips per foot, and it was 8 foot spanning, right? So this says the peak value there will be W, which is the 3 kip foot, length of the span, which is 8 squared, over 8. Okay, so now if you evaluate that, it should be 24. So 3 times 8 squared over 8. So 24. So if you were to have a test on this material, you could be pretty confident that you could use this sort of a table as a guide, whether you're on the right track or not. And this also shows you that like this is a positive direction up here in the moment, and I didn't detail too much, but I really expect that we would be pivoting on the left point, the leftmost point for these charts. So yeah, this one's really interesting. It shows these reactions are the same as these two loads that are separated. And so your shear diagram is the reaction at first, comes over, canceled out entirely. And so there's no shear in between these two loads that are, I assume, the same distance apart, A. That's a really weird scenario. And I really want to show an example of cantilever. And in this book, for some reason, they don't have the charts for it. So I'm going to go ahead and let's do example 1311 because I want to see the diagram. And it doesn't use the diagram, it uses the charts to cheat and just get the maximum moment and shear. But you're going to want to be able to come up with charts on cantilevers at some point. So let's go in this direction. And has a point load of 8 and a distributed load of 1.5. Okay, and this is 2 meters. 2 meters. Okay. So first off, I want my reaction. And with a cantilever, it's not simply supported. It has all of its reactions in one location, x and y. So this is y, x, and it also is going to have a moment reaction because both of these loads are causing a positive moment. We're going to have a negative moment reaction. So I'm going to call that, I'm just going to call it moment reaction. I'm okay with that. Did they call these points anything? Nope. Let's just call this reaction x, reaction y. Reaction x is going to be 0 because there's no horizontal loads. Sum of forces in the y will actually give me one unknown. So -8 minus 3, because that's 2 meters, 1.5 kilonewtons each meter, plus Ry. So Ry is 11. Okay. And now my sum of moments are very strange, but let's do it about this point over here. I don't know what. They need to be 0. And I'm going to have a point load of 3 that is 3 meters away from the point I just randomly chose. So 3 meters, 3 kilonewtons. And then I'm going to have a reaction that's 4 away. I already know it's going to be in the negative direction, so I'm just, I guess, whatever. And it's just a moment reaction, and it's not at a distance, it's like instantaneous, if that isn't crazy. So R is equal to -9 kilonewton meters. So that describes my entire system. I have a vertical force of 11 and no horizontal force. I have a -9 kilonewton meter. Then I have a -8 kilonewton and a distributed load. And for fun, this is 1.5 kilonewton per meter. I want to check if I got my sum of moments to be 0 doing this. So I'm going to do a sanity check. So I'm going to do my sum of moments. Let's go right here in the middle. This is 2, 2. Okay. Center. I want it to be 0. So I've got positive 2 meters times 8 kilonewton. Positive 1 meter, 3 kilonewton. 2 meter. Uh oh, I drew this arrow backwards. Because this is positive this way. Positive. Okay, down. Now I'm going to have a negative. No, it's still positive. Everything's positive. This one's negative. Okay, sorry. Negative, positive, negative. Okay. So positive 2 meters times 11 kilonewton minus 9. Okay. 16 minus 3 plus 22 minus 9. That does not come to 0. Positive, negative, positive, negative. Okay. Oh gosh, I missed it up here. This 11 at 4 is positive. Okay. Okay, let's start over. Okay, so this is 9, 44. It's a lot higher. That'd be 55? No, 53. It's still pretty bizarre. We got these signs wrong. Right, one is up and one is down. Doing it at 0, so this one, okay, yeah. Like that. It's 11 and 3. Three to here, 4 to here. Yeah, I just need to be more careful. I'm trying to go too fast, which ultimately takes up more time. So this is a negative 3 kilonewton. This one is a positive 4, 11 kilonewtons. And then I've also got my moment reaction. I'm going to assume positive, but it'll end up being negative when I subtract 44 plus 9. So then I end up with what, 35? Which sounds a lot better. Kilonewton meter, that's negative. That's my moment reaction. So plug that into the same check. So moment center. I'm just going to go back into where I found it was wrong here and change my 9. To minus 3.5. Where's my calculator when I need it? Oh, buried in the paper. Okay, so 16 minus 3 plus 22 minus 35. 0, yay! Okay, so now my reactions are known. I'm going to summarize them on a new page so I can draw my diagrams in one page. I've got a simply supported beam with 11 up. Negative is this direction. Got 8 down. 35. Instantaneous moment. And 1.5 distributed. Kilonewton per meter. Okay, kilonewton. This one's kilonewton times meter. 35 kilonewton meters. Okay. Let's go for shear diagram now. So minus 8. It does nothing until this point. Let's call that at this line, huh? And that was 2 meters across. This is a minus 8 kilonewtons. Now it has a negative distributed load. So I'm going to keep going negative at a rate of 1.5 per meter. Let's see, I just called a meter 4 squares. So let's do 4 squares. I'm going to drop 1.5. So I'm going to be at negative 9.5. And then I'm going to drop another 1.5 down to 11. And then I'm going to go up 11 to 0. Okay. So now, because I'm thinking of my moment diagram as pivoting around like the left side here, I think my moment diagram is going to be all negative, basically. And then there's just going to be a large discontinuous moment at the end here to bring it back up to 0. From basically like in the wall to be 0. But it'll be 35 out here. Let me check it. Yeah, so it'll look a lot like this guy. See, it has a distribution, and then its shear is somewhat. So it's kind of a combination of these two. So its moment is going to look kind of like that. So it's going to peak right at the wall. So if this were to fail, it would be right at the support. So the moment is going to be some of this area. So this box, let's do that one first, is 1 meter across and 8 high. So we're going to be at, let's call this 8. One box is 8. Then the next one is going to be 16. It's going to be all of that. So let's go down another one here. This is our 0. Okay, and now it starts. You still have these 8 increments, but you also now have these triangles on top of that. So each one of these boxes was 8, 8. So we're going to still almost go down by 1 square, but we're going to have a little extra there. And those little triangles were, the first one was 1.5 tall and 1 across. So it's only 1.5 extra. Okay, so this is -8 kilonewton meter, -16 kilonewton meter, and now we're at something extra. So 25.5. Okay, and then this next extra is, what was that? It's like 2. It's a combination of 2 squares. No, it's a triangle and a square. This one's 1.5 tall, 1.5 tall. 1 across. So, oh gosh, that's supposed to be half of that. No. Gosh, 0.75. So I should have only added 0.75 to 16. Okay, so this one's 1.5, 0.75. I think. So this, so maybe it's drawn badly, but this triangle should be the same size as that triangle, because the height is only 1.5. Okay, let me correct. 16, 24, 24.75. Okay. And it's negative. And then the next one is 24.75 plus this whole segment here to get down to there. And it should be 35, was it? So let's see. So this is, okay, I've got, 875. Like that. So that should add up to 35. Cool. It does. So right at the end here, should be down in the 35. 1, 2. And so what this was a straight line here, and then it was a straight line plus a little bit of a parabola there. And then right here at negative 35, we have that 35 reaction that should take us home. Cool. Which makes me wonder if my reaction was actually positive. Let me look at that again. So this is a positive reaction, and the wall should be negative. Okay. And so you could use the formulas to get that, is what this is saying. PL plus WA squared over 2. So basically they had to combine these two. Okay. Summary of the chapter. Okay. So with that, I'm going to assign this problem 13.3, and these are really long problems, so I would budget an hour. Oh, this one says determine reactions. I kind of want you to do the diagram. Okay. But these are a lot more complicated. So it could take longer. And this one's ramping, so it'll end up with a parabolic. I kind of want you to do a simpler, because it's already going to take forever. Okay, yeah, do this one, but do the shear diagram on it. Okay. So 13.3 shear and bending diagram. And then I want a simply supported beam. Oh, that one's cool. But these are only shears at certain points. I'm sure we could find one that's better. One thing to note is in this particular example, there will be a moment at this support, and you can see that in the cheat. Guess you can't. But there's no moment at the end here. But there is a moment in the beam at the support if it's overhang. Let's see. Draw shear force and bending moment. Locate section with 0 force, if any. Okay, let's do this. This is 1316. Am I pointing at the wrong one? I actually wanted 13 for 1316. Okay. And this should be about 2 hours. I think that wraps it up with all of the required assignments. Just that one right there. I think I'm going to go on to do bonus material that you don't have any assignments with in chapter 14. I think, yes. Okay, we're doing this next.